Thank you, Naveen, Pradeep, everybody at Stony Brook for inviting me and for organizing this conference online. I'm going to present joint work with Demian Puso and with Yuichi Yamamoto. And this is work on misspecified models, agents who have misspecified models. So let me start with some motivation, 2 sentences that I hope we can all agree on, that models are an approximation to the truth, and that the world is pretty complex, and it is pretty natural for people like us, researchers, to represent this uncertainty about the world with parsimonious models that are likely to be misspecified. Now, if you're okay with these statements, all I ask is that you grant me the possibility to change the word researchers with economic agents. That is, that we also allow the possibility that the economic agents that we're trying to understand and model, also themselves have to tackle this complexity, and they may themselves come up with parsimonious models to understand the world, environment, that are likely to be misspecified. That is pretty much the motivation of this literature about agents who have misspecified models. And over the recent years, we've seen a lot of applications where, in very different areas. We have some early examples on demand estimation by Arrow and Green and Kerman, and a paper in the 90s by Niarko, which are mostly examples. But since then, we've seen many applications. For example, the recent work on overconfidence by Philippe Jehiel and Hughes, Kosegi, and Strack, how people respond to taxes, the law of small numbers and the hot hand fallacy. We have applications in macroeconomics. We have Rani Spiegler's work on Bayesian networks and the work he presented earlier this morning. We have work on discrimination, such as the one that Aisling was presenting, political polarization, and a growing literature on social learning. Agents who are not, they're somehow misspecified when it comes to learning from the actions of other agents, where also Aisling has contributed a lot to this literature. So for those of you who are not familiar with this literature, let me just mention 2 examples. One is a toy example about demand estimation. So suppose we have some firms and their sales depend on their own price and also on the price of the competitors, plus some random demand shock. Okay. But prices are not observed. In particular, there's a large firm out there that does not observe the price of the competitors, and therefore decides to ignore the prices of other firms and estimate a demand model where sales only depend on its own price. This is clearly simplification. To the extent this firm is very large, this is a close approximation to reality, but of course there's going to be some biased estimation of the parameters, because there's omitted variable bias, prices of other firms are not being included. Okay. A more recent, a more fully developed application on overconfidence is an econometrical paper by Hughes, Kosegi, and Strack. Here we have a worker, and the output of this worker depends on his ability and the ability of a teammate, and also how much the worker decides to delegate to his teammate. So the decision here is how much to delegate the work to the teammate and how much to do it myself. The worker is going to be learning about the teammate's ability by observing output, but this learning is going to be biased because the worker is overconfident about his own ability. So the question is, how does this overconfidence about my own ability biases my learning about the ability of the other agent, and consequently the decisions, the delegation decisions that I make in this environment. So this is just 2 examples to give you a sense of this literature for those of you who are not familiar with that. Let me now move on to what is the main question that we have and that the literature is trying to answer from a more theoretical perspective. In the previous examples, there's an agent who processes information through the lens of a simple model that misses some aspect of reality. And in many of these applications, the direction of the bias is not ex-ante obvious. And the reason it's not obvious is because of the following. You have an agent, and the agent's behavior depends on the feedback that they receive. Now, at the same time, this feedback is going to be processed via a misspecified model, right? And once you process that feedback, that's going to lead to updated beliefs. These updated beliefs, in turn, is going to lead to changes in behavior and so on, right? So the question is, okay, eventually, what can we say? Does this behavior settle down? What can we say about the beliefs of the agent and the behavior of the agent in such a world? And one reason why I like this sort of a framework with misspecified agents is because of many of the applications, there's a separation between the assumptions that you make about what is it that the agent is simplifying about the world, what is the misspecification of the agent, and the results. That is, what is the agent's behavior and beliefs, right? So rather than just assuming, oh, the agent has this particular biased beliefs in this direction or that direction, this kind of framework allows you to say, okay, this is how I think the agent doesn't understand the world. This is the kind of the mistake they make. Okay, now tell me as a result of that mistake, what is the eventual behavior and beliefs? And in many of these applications, there is a separation there. It's not obvious ex ante, how the misspecification affects behavior, precisely because of this channel that I'm describing here in a very vague way, which is the fact that behavior affects feedback, feedback processed through a misspecified model leads to beliefs, beliefs then in turn change behavior, and this continues and starts over again, right? So one of the questions that the literature asks is, what can we say about beliefs and behavior in the limit as time goes to infinity? And that is the question we're going to try to answer in a general way with some general techniques in this paper. Now, why in the limit as time goes to infinity? There are several reasons for that. Let me mention just two reasons. One is there's a tradition in economics, which is the equilibrium tradition. The idea to focus on equilibrium behavior, a steady state behavior, right? And I think that is very convenient. And also it gives you tractability in the analysis. So that's one reason. The second reason for looking at asymptotic behavior and beliefs is because we're interested in biases that persist. We're interested if there's any systematic deviation from optimal behavior, not when people are inexperienced or maybe they have not received enough feedback, but after people have actually experimented with a lot of feedback and have received a lot of information about the environment they're in. Okay, so these are two reasons to motivate why, there's obviously a third reason that is much, we have the tools to think about, asymptotic analysis, and it's much harder to say something about the dynamics leading to that, right? And, especially in the short term. So that's obviously another reason for that. Okay, so what do we currently know about this question of characterizing asymptotic beliefs and behavior? In previous work with Damian Puso, we showed that many of the examples in the literature fit within a common framework, and we provided a characterization of steady states. So roughly speaking, the result that we showed, the main result in that paper, is that if the action of the agent converges, then it converges to what we called a Brook-Nash equilibrium. And we also, we can also talk about mixed strategies, but for now it's simpler to just think about pure actions. So that's something that we did in earlier work.
How does it differ from Nash equilibrium?
I'm going to show you in a second. But basically, you can think of Nash. First of all, let me clarify a few things. Today, I'm going to talk about a single agent framework. There's only a single agent, so it's a decision problem. In this paper, we also consider multiple agents. And when you consider multiple agents, we consider a game environment. A Nash equilibrium will be a special case of a Brook-Nash equilibrium where the agents have a correctly specified model. And there's a property that holds called identification.
Okay.
Mm-hmm. But in general, the idea would be that your beliefs could be, in Nash, beliefs are correct. In this sort of solution concept, Brook-Nash, your beliefs could possibly be incorrect, but they cannot be anything. They still have to be pretty, grounded by, the behavior that agents are taken, and also by the model that they're using to understand that behavior. Okay, but I'm gonna show an example, a more concrete example about what Brook-Nash is in a second.
So it seems related to self-confirming equilibrium. They agree on what you can see, but their conjectures on counterfactuals can be different.
Exactly. In fact, self-confirming is also a special case of Brook-Nash, where I maintain the assumption that you are correctly specified, but now I don't necessarily assume that you have identification.
Okay.
But these are things that are from previous works. I'm not going to spend too much time talking about these things now. I just wanted to give you kind of the message to take from this paragraph is that we have a result characterizing steady states. if behavior converges, we can tell you what it must look like. And basically, it's got to be a Brook-Nash equilibrium.
Thank you.
But the emphasis of this paper and the subsequent literature, theoretical literature, was on, okay, but what do we know about conversions? Do we get to the equilibrium or not? Are some equilibria stable or unstable, and how can we tell? So there we had very few results. We had actually an example by Niarco from the early 90s, where he shows an example when an agent is misspecified, and in that case, actions do not converge. But until recently, we knew very little about conversions in general, or what happens if the actions do not converge. Now, over the last few years, we've seen a lot of progress in this area. The first few papers to tackle this idea of conversions, this question of conversions, made assumptions. They assumed, for example, either the prior belief has a finite support, or they made a specific functional form assumptions. And this is basically a series of papers by Philippe Strack with co-authors Friedenberg, Romaniuk, Haidt-Hughes, and Kosegi. And then here's where a paper comes in, trying to establish more general results. And in addition to our paper, at the same time, we have two other papers, really nice, interesting papers, trying to establish more general results, relax some of the previous assumptions to establish conversions. One is by Mira Frick and Ijima and Ishii, which I think are here today. I think I might have seen them. So in their paper, they focus on conversions of beliefs, conditions under which you can guarantee that beliefs converge. And they also, they have a really nice part of the paper that looks at robustness to small misspecifications. And they show that under some conditions in some settings, even very small misspecifications, lead to behavior that is very different, or beliefs that is very different from the ones you would have if the agent had a correctly specified model. And the second paper is a recent paper by Friedenberg, Lanzani, and Strack. Their focus is on conversions of actions. And what they basically show, roughly speaking, is that, look, there's some Brook-Nash equilibria to which you are not going to be conversion to. And there's some to which you will converge with positive probability. So that basically motivates a refinement of Brook-Nash equilibria. A refinement, some Nash equilibria, that you can basically, show under some conditions you're going to be conversion to, and some others you can basically throw out. So for example, in some cases, you do have multiplicity of equilibria. So that helps in terms of, selecting among those multiple equilibria. What we do in the current paper is we're going to use very different tools. We're going to use tools from a stochastic approximation. These are tools that have been developed over many years by Benaim and others, and in particular, a recent paper by Benaim, Hochbauer, and Sorin. And these tools are going to allow us to develop a general method to obtain asymptotic characterization of beliefs and behavior, irrespective of whether behavior or actions converge, or irrespective of whether beliefs converge. Just follow, characterize the evolution of this behavior and beliefs of this agent using a stochastic approximation methods. Now, I won't have time to show you everything. Obviously, I just want to give you kind of a brief overview of what it is that we do, and hopefully that drives people who are interested into reading the paper. We promise we'll have a nicer version to read soon, hopefully. But kind of the bottom line is that if you're interested in applying these techniques, now you have a lot of results you can use from many different papers where you can hopefully use to easily characterize what happens to the agent's behavior. Does it converge or not, or what does it converge to? Okay, so that's kind of the message for those who are trying to apply these techniques, apply these models with misspecified agents with misspecified models. Okay, let me briefly now go into some specifics, tell you about at least the environment. And this is kind of the simplest environment I can think of to describe what it is that we do. There's going to be just a single agent today, just one agent. The agent faces an infinitely repeated decision problem, and time is discrete. So each period t, the agent is going to choose an action xt from a finite set of actions. And as a result of the action xt, there's going to be some consequence y that is going to be drawn according to some probability distribution q given xt. Okay, this is the true q, the true probability distribution given xt. And then the agent receives a payoff that depends on the action they take and the consequence. Now, if this were it, then basically the agent would say, if the agent knew the primitives, they would maximize expected utility, and they would choose an action that maximizes that expression. The twist here is that the agent is not going to know what the Q is. The Q is something the agent will not know. So the agent will be Bayesian, and the agent will have a prior over a possible set of Qs, a possible set of consequence functions. We're going to assume that the agent has a parametric model in the sense that we can index these consequence functions Q by a parameter theta, where this set theta is a compact subset of a finite dimensional Euclidean space. This is what makes it a parametric problem, as opposed to a non-parametric problem, the finite dimensionality. And as usual in this literature, you know, for parametric assumptions, we're going to assume that Q theta is continuous. As I said earlier, we're going to assume the agent has a prior. Here, let's say the agent has a full support prior over this parameter space. So, you know, the agent starts with a prior, takes an action, observes a consequence, and then takes, you know, that consequence and uses it to update the beliefs over the parameter space. Okay, and this continues, you know, indefinitely. So here I can now formally define what I mean by misspecified. I have been saying these words without any formal definition. The agent's model is misspecified if the true probability distribution Q that I showed you in the previous slide, okay, is not in this set of Q thetas. In other words, you know, it's not in the support of a prior. And otherwise, we say the agent is correctly specified. So for those of you who are familiar with the correctly specified case, this is just the setting that, you know, Isley and Kiefer and Aguillon et al. Study, the correctly specified case. Okay. We also make some regularity assumptions that I'm going to skip here. There's some technical assumptions that I'm going to skip. So just to focus the idea, let me give you a very simple example. It's a matching problem. There are two actions and two states. The objective of the agent is to match the action with the state. Hey, if I know the state is going to be A, I want to choose action A. If I know the state is going to be B, I want to choose action B. Okay, that's the objective. The agent has a subjective model. The agent believes that the probability that the state is B does not depend on the action, whether the action is XA or XB. And that probability is given by theta. And it can be anything between 0 and 1. Now, this is going to be a misspecified model because the true model is that indeed the probability that the state is B does depend on the agent's action. In other words, the agent believes that he faces a pure matching problem, just try to match the state and try to learn what the probability distribution is over the state A and B. But in reality, this agent, by choosing an action, you know, has control over the state of the world. Okay, so very simple problem. Even in this problem, we know already that it is possible that the action does not converge. I'm going to show you that, you know, if I make assumptions on this Q, the true Q, natural assumptions, the action doesn't converge. But we don't know more than that. Using existing tools, we don't know more than that. I'm going to show you that it is possible to show that even though the action doesn't converge, the frequency of actions does converge for this agent. Okay, so the steady state will look like a mixed strategy, and the behavior will converge to this mixed strategy. Okay, I'm going to show you that using these techniques, and that's something that you cannot show using other techniques.
Ignacio, can I ask
yes.
you a very quick question? It looks like, so essentially you're assuming that the truth does not belong to the set of possible states of the world that you can figure out. Now, would it really change a lot for your results if you were to allow the truth to belong to a set of states of the world, but with a vanishing probability?
So again, it depends on the application. So as Mira Frick and her co-authors have shown, in some cases, it does make a big difference if you assume a small misspecifications, you know, versus no misspecification. In other cases, it doesn't, and things are fairly robust to a small misspecifications. Here in this example, I'm going to assume like a large misspecification. Now, you also ask me if the techniques that we're showing here, you know, to what extent do we rely on being misspecified? We don't. I mean, what I show you here can be used for the correctly specified case or for the misspecified case. I think we have a better understanding of the correctly specified case, Aguillon et al. And Isley and Kiefer, but it could in principle use these techniques also for that correctly specified world. But I'm more motivated by, you know, all the applications that we've having recently that are having agents with misspecified models. Yeah, but there's nothing here that, you know, the techniques I'm going to show you hold also when the agent is correctly specified.
Thank you.
just one clarification. When you say the frequencies converge, do the oscillations also become steady, or that can be crazy?
I'm gonna show you yes, I'm not looking at that. I'm looking just at the frequency. But let me get there. When we get there, we can maybe talk about that. Okay. Yeah. Okay, just very briefly, I don't want to overwhelm you with notation, but it's exactly what you can expect. There's going to be some policy function f that maps beliefs, right? These are the agent's beliefs into actions, and then basically a policy function f generates a probability distribution over histories, and so the results will be stated, almost surely with respect to this probability distribution. So just think of the agent using some policy function f. Something that is interesting here is that we are going to look at policy correspondences. Not necessarily just policies, but policy correspondences. And we're going to think of the agent's policy as being a selection from a policy correspondence. And our assumption on behavior is going to be that the selection from this policy correspondence is such that the policy correspondence is upper continuous. That's kind of a regularity assumption we're going to make on the agent's behavior. Okay. Now, this is some assumption that comes for free if you want to assume the agent is optimizing. So, for example, if the agent is maximizing discounted expected utility, this is the Bellman equation for this problem, where the belief is a state variable. It's a fairly complicated problem to solve for the agent, right? Well, you can assume that the agent is doing this, or you can instead assume the agent is just following some kind of heuristic policy function f, as long as f is a selection from an upper continuous correspondence. Okay, but again, optimization is a special case of this, but you don't have to assume the agent is optimizing to use our techniques. Okay, why frequencies? So it turns out frequencies for the following reason. Even if actions do not converge, we can show that in many cases the frequency converges, and we can think of this as an interpretation of mixed strategies, right? A second reason is that, as we show, although I'm not going to do a very good job showing this because of time constraints here, but as we show in the paper, beliefs asymptotically depend on the action frequency. To characterize beliefs, it's sufficient to just know what has been the action frequency at that point. As time goes to infinity. Because actions in turn depend on beliefs, then future actions depend crucially on the frequency of past actions. So frequencies play an important role in these types of environments. So it's natural to think about frequencies and not just about either actions or beliefs. In particular, it is possible for actions not to converge, but the frequency converges. It is possible for beliefs not to converge, but the frequency of actions converges. Okay, so this is the reason why we look at frequencies. So what is the definition of a frequency? This is exactly what you can imagine, but the notation will be sigma t h. H is the history. So sigma t h x is giving history h. What is the frequency of times that you have observed action x up to time t? Okay, so sigma t will be notation for this frequency of actions. Okay, and it's something that lives in this delta x. It's a probability distribution over x, the sigma t. Okay, so what is it that we do? Let me jump straight to the result and try to maybe tell you a little bit about how we prove that result. First, one definition. Those who are familiar with the literature have seen this many times. Kullback-Leibler divergence plays a prominent role here. What is Kullback-Leibler divergence? So this is a function k that here depends on the parameter theta and sigma, a probability distribution over actions. To focus idea, you can think of this as some kind of a steady state distribution over actions the agent chooses, right? Just to interpret this. And this is essentially the expectation of a log likelihood ratio. So we know from statistics, the expectation of a log likelihood ratio tells us something about the goodness of fit, how good of a fit is model Q theta when the truth is given by Q, right? So this is what it is, except that now we're weighting this by sigma x, right? The agent isn't just always choosing the same action x. It is possibly the agent that chooses sometimes, half the time chooses one action, half the time chooses the other action. So you have to weigh this expected likelihood ratio in that way. So the interpretation of this Kullback-Leibler divergence is that it sort of measures some kind of a distance of goodness of fit between the model theta and the true model Q, right? Whenever the agent behaves following sigma, okay? And a piece of notation to remember is I'm going to use theta sigma as a set of minimizers of Kullback-Leibler divergence. This is the set of parameter values that minimize the Kullback-Leibler, which are basically the ones that are a closest fit, the parameter values that are closest fit to a true model, and that depends on the sigma. So here's going back to the example to show you how this is something very intuitive in many applications, such as in this one. Remember that this agent believes that the probability of B does not depend on his own action. It's just theta. The true model indeed is that it does depend on the true action. So Kullback-Leibler diversions, you can write it down. That's what I did here. And essentially you can show that there's a unique minimizer. So the unique minimizer is basically a weighted average of the probability of B given action A and the probability of B given action B. Right? And this is fairly intuitive. The agent believes that doesn't depend on the action. So then what the agent learns at the end of the day, or the parameter that best fits the data, is one that is a weighted average. How often did the agent choose action A? Then it's QB of A that is valid. How often did the agent choose action B? Then it's a QB that is valid. So it's a weighted average of those two that gives rise to the best fit parameter from the agent's perspective. Okay, so yeah. Okay, so let me now show you how we proceed. The objective then is to say something about this frequency of actions, this sigma t, right? It's a random variable, to say something how it evolves over time. So we're going to use a stochastic approximation technique. So we're going to basically approximate this discrete system, sigma t, by its continuous time interpolation. Now you can ignore the equation. This is the picture of what we're doing here. We're going to call W the continuous time interpolation of the sigmas, this frequency of actions. And basically what we're doing, we're doing a linear interpolation. And we're basically decreasing the time intervals over time. And we're making sure that we cover the entire time, entire real axis all the way to infinity. Okay, so now we're going to say something about this continuous function, this continuous time function. And obviously, if we learn something on this continuous time function, if we learn, for example, what are the accumulation points, then we'll learn also what are the accumulation points for the one that we care about, which is the discrete sequence of frequency of actions. Okay, so why do we do this continuous time interpolation? Because we want to relate this to a particular differential equation or inclusion. Okay, so let me now show you that differential inclusion. So what is a differential inclusion? It's a generalization of the differential equation where the derivative can take multiple values. Okay, so it turns out that this equation 1 is going to be our differential inclusion of interest. So let me go slowly over this thing in the middle. I wish I could highlight, but hopefully, can you see my my cursor? Okay, that's great. I cannot highlight it, but at least you can see where I'm moving. Oh, I don't know what happened with that. Okay. Okay, so let's look at this expression, and let's look from the inside out. So here we have theta sigma t. So sigma t is the current frequency of actions at time t. And theta sigma t is, if you take that frequency of actions into account, what are the set of parameter values and minimize Kullback-Leibler divergence. Okay, let's say for simplicity that this is like in the example, we have a singleton. So we have basically a unique value that minimizes Kullback-Leibler divergence. So then you can ignore the delta here. Okay, we just have a single parameter value here. So what is f of that single parameter value? That's basically what is the optimal action given that parameter value, right? And in that case, in general, you will have basically that there's a unique action that is optimal given some belief that puts probability 1 on the parameter value. But there's a specific, there's a possibility as well, that you have a belief for which you're exactly indifferent between the two actions. And then, this delta, allows for all possible mixtures between the actions on which you're indifferent, right? But if we're only looking at the case where we have a singleton minimizer, so theta sigma is a singleton, and given that degenerate belief on that parameter value, there's a unique optimal action, then this is not a set, but this is basically a unique action, and this would have an equality here. So this would be exactly a differential equation. The reason we need to allow for differential inclusions is precisely for the possibility that there's more than a unique minimizer, and also for the possibility that even if there were a unique minimizer, there's some beliefs under which the agent might be indifferent between two or more actions. Okay? Okay, great. So this is the differential inclusion, and we can define solutions to differential inclusions. And let's just denote S T sigma as the set of solutions to this differential inclusion from initial condition sigma and going all the way from time 0 to time capital T. Okay? So now let me show you the main result, the main technical result, and it's really ugly. And if I had more time to explain it, I would be able to do a better job. But let me just say it in words to give you kind of an idea what this thing says.
I have a technical question.
Yes.
On that differential inclusion, in the cases that you look at, is it single valued for almost all t and breaks up into a set only when measure 0 of time, or more robustly?
Yeah, kind of yes, if you have identification, which essentially means it's a single unique minimizer.
Most of the time.
Yeah, yes, but there are many examples where you have there's no identification and theta sigma is itself a set. So in those cases, you would not have you wouldn't have that generically.
Okay.
Yes, yeah, and and this basically we will cover all the cases in this case with this expression.
Okay, thank you.
Sure. So what is this theorem telling us? And it's the main theorem in the paper, but obviously there's a lot of work that comes after this theorem. The theorem basically says, give me any capital T, as large as you want, and then the curve W T plus, that goes from 0 to T. So starting from some time T, and this T here that is in the W will be a very, very large time, not any time, but a very large time. And remember, W is the continuous time interpolation. So it's basically the object we care about. We want to characterize exactly what does this continuous time interpolation of action frequencies look like. So that curve, which is the continuous time interpolation, approximates some solution. That explains the inf in the expression. Some solution, there could be multiple solutions of a differential inclusion, right? That's the thing I should have mentioned in the previous slide, that, contrary to differential equations, that under some conditions there's a unique solution, Lipschitz continuity. For differential inclusions, you actually, as you can expect, because they have a set of possible values the derivative can take, you could have multiple solutions. So that explains why you have the inf in this expression. Okay, so this continuous time interpolation W, the object we care about, approximates some solution to the differential inclusion that I showed you in the previous slide with the initial condition WT over the interval 0 to capital T with arbitrary accuracy for sufficiently large T. So, in English, this means that we can obtain asymptotic characterization of the frequency of actions by solving the differential inclusion. Okay. Now, obviously, in some applications, it's not so easy to solve the differential inclusions. So what we have then is a series of results to help people apply this theorem. Okay. Now let me just go back to the example to maybe this kind of shows Pradeep, it shows what this looks like in the context of example, and it's exactly what you had in mind in the example. We have this differential inclusion, and notice that now this theta sigma has become a small theta sigma, which is a unique minimizer that I showed you earlier. So basically this delta is the Dirac measures, putting probability 1 on that minimizer theta sigma T. And F of that is basically the action the agent takes. So what do we know about theta sigma? I showed in the previous slide, theta sigma is the weighted average of the QBs given action A and action B, and the weights are given by your behavior, hence beliefs are endogenous to behavior. And what is the F? Let's say in this problem, well, I told you what the objective was. In this problem, basically, you're going to pick action A if you believe theta is less than a half, and you believe action B if you believe theta is higher than a half. This is goes with the matching objective that I showed you earlier. And of course, there's a point of indifference, right? If you believe theta is exactly equal to a half, then you're exactly indifference between XA and XB. So let's say now that I assume that QB of action B is less than a half, and QB of action QB given action A is higher than a half. Okay, I make this assumption on the primitives. So this is what this expression looks like. This is the delta F of, that this is this part here. And this is what it looks like. To interpret this, let's suppose that we have an agent who is picking some, the frequency of B is fairly low. It's around here. Well, the frequency is fairly low. If that's the case, then you put little weight on QB given XB, and you're putting most of the weight on QB given XA. QB given XA is higher than a half. So this agent comes to believe that theta is higher than a half. And this agent therefore wants to choose, for sure, action B. So therefore, that explains that going all the way up here to choosing action B with probability 1. And similarly, if this agent is choosing action B with a very high probability, then a lot of the weight now is on this expression QB given XB, which is less than a half, right? And then the agent comes to believe that, okay, the theta is less than a half, but then the agent wants to go ahead and choose action A. So that means the optimal thing to do is to choose B with probability 0. That explains this segment of the red line. And here exactly there's a point of indifference at which basically you're indifferent between any of these actions.
So Ignacio, you have 10 minutes. You might want to leave a few at the end for discussion.
Thank you. Thanks a lot, brother. Appreciate it. Okay, so then if I just look at the differential inclusion, it's basically a differential equation. The multiplicity only happens at that point, but it's inconsequential to kind of understand the evolution of this system. Starting from any initial condition, you will converge to the sigma star xp, right? So you can use the previous theorem to show that in this world, under these assumptions, the action doesn't converge, but the frequency of actions converges to the sigma star xp. Okay, what exactly this value is, can be characterized. Obviously, depends on the Q, the true Q, right? Okay, it's just a picture. So this is a sort of techniques that you can use to say something about behavior and conversions of behavior and beliefs. By the way, in this example, if I assume that theta is not the 0-1 interval, but I assume that theta only takes 2 values, then the same picture would hold, but then you wouldn't even have conversions of beliefs. So it would be a situation where there's no conversion of actions, no conversions of beliefs, but the frequency of actions does converge in this case. Okay, but I don't have the time to show you that, but I wanted to at least mention that. Okay, the sketch proof of the theorem. I have very little time, but I want to at least show you how it is that we prove something like this. The first insight is basically being familiar with the stochastic fictitious play, Friedenberg and Krebs, the literature in the 90s, and understanding how you can write frequencies in this manner, the frequencies of actions. Tomorrow is a frequency today, but plus some innovation term. That is basically the indicator function of what action you take today minus the frequency of actions at time t. And this is something that is common in that literature on stochastic fictitious play and the literature on stochastic approximation. The next step, which is also from a stochastic approximation, is to add and subtract the conditional expectation of this indicator function. So then basically we'll have an expectation of the indicator function given the belief minus sigma t. And then this term, let's ignore it. In the case where you take a pure action, this goes away. If you allow for mixed actions, we can also make this go away. So this is like noise, a noise term. So let's forget about that. And then the next step is to say, okay, in this expression, I have this expectation of the indicator function depends on the belief. If I could somehow relate the belief to the frequency of actions, then I have written an expression, a difference equation that only depends on frequency of actions, right? So the goal is to be able to write down these beliefs, approximate this belief mu t plus 1 by something that has to do with the frequency of actions. And that's kind of, a theorem that we have in the paper. That's something that we have. I don't have time to show you here the details, but that's essentially how this works. And this is what leads to the differential inclusion. Then the last step is to go from our discrete system to the continuous time system. And there's when we borrow techniques from Benheim, Hofbauer, and Sorin, from that paper. Okay, but anyway, so what do we do in the paper? The theorem is not very friendly. It's not easy to use. So then we have a whole section where we try to make it more friendly. We basically define an equilibrium in this framework. We basically show you that, behavior has to converge to an equilibrium. We then define the notion of an attracting equilibrium, a basing of attraction, the notion of globally attracting. So in that example, the example I show you that there was a single unique equilibrium and it was globally attracting. So now we have a theorem that says, okay, if there's a unique single globally attracting equilibrium, then you always converge to it almost surely. But what happens if you have multiple ones and so on? So you have all these different results that basically are a corollary of the main theorem. And the other thing that we do, we all look at repelling equilibrium. We also look at the special case where theta is one-dimensional. This is very typical in the literature to have a one-dimensional theta. And in that case, there's more things we can say about this environment. Again, using these tools from a stochastic approximation, using the theorem that I showed you earlier. Let me skip this. Let me just conclude so I have time for questions. Modeling agents with misspecified models have become more prevalent in economics. What we do here is develop general techniques that can be used to characterize beliefs and actions as time goes to infinity in a large class of settings. The key insight is really to focus on the action frequency. That's a key insight. That's a key element in this sort of environments. We can think of a new interpretation of mixing in terms of converging to conversions of the action frequency. And there's something I didn't talk much about, but it also, it turns out there's some equilibria that are not Nash-like that can arise as well here under some conditions as well, but I didn't have time to talk about that. And the goal here again is to have this work to make it easier for people to apply, do more applied work in these sort of environments, and have off-the-shelf results they can use to show conversions or stability or lack of stability of equilibria in these sort of environments. Okay, that's it. Thanks.
So here is a question from Kuimin Ba. Please forgive me if I'm pronouncing your name wrong. So I'm now reading it out. A technical question. Can the assumption of a finite action space be relaxed, e.g. continuum? It does seem that some parts of the proof, even the formulation of an action frequency, will rely heavily on this assumption.
Yes, that's a great question. And the answer is pretty much no. I wouldn't know how to do it. We haven't done it. This is an environment in which there's a finite number of actions. And in a way, the idea of even thinking about frequency of actions, you know, as you saw from that equation that I show you, is relying on that. Now, could it be generalized? We would have to use, you know, tools from a stochastic approximation that I'm not familiar with at the moment. Maybe it could be generalized, but you know, we haven't done it. So in a way, you know, most of the applications that I know of are using finite actions, but there are some applications that use a continuum of actions. And I would say for those applications, then the tools that we develop here wouldn't be directly applicable at this moment.
Any other questions? I mean, we have 4 minutes left because our speaker went so efficiently on time. If we don't, then
Pradeep, I have a question. So
go ahead.
it was a great talk. So maybe you were alluding to this in the last slide and I missed it, but are you suggesting that these techniques are portable to games?
Okay, so I didn't say that, but let me say it now. Yes, the answer is yes. So in the first paper we wrote with Demian on this, we actually had multiple players and we characterized steady states with multiple players. In the paper here that we have with Yuichi, you know, for simplicity, to simplify things, we're only looking at decision problems with a single agent. But it could, in principle, think of this sigma. You know, this sigma is a vector, and this can be a vector, and you know, and we can basically think, you know, there's a sigma superscript I that indexes basically the frequency of actions of player I, and you have the frequency of action of player J, and you can actually use these tools to look at problems with multiple agents. So that is something that will be possible to do as well. Yes. Mm-hmm.
Well,